It's my great pleasure today to welcome Professor Tim Jones to our department. For those of you who might know our recently graduated colleague Graham Morris, Tim served as his external appraiser for his PhD. And so it's with great pleasure that I can introduce him. He got his BSc in 1985 and his PhD in 88 from the University of Liverpool in the discipline of chemistry. After a postdoctoral fellowship and a little time with a startup in industry, he returned as a lecturer, first as a reader in the Department of Chemistry at Imperial College in London in 1996. 1997, he was promoted, 96, he was promoted to reader, 97 to full professor of chemical physics. In 2007, he moved to University of Warwick and is now a professor of chemistry and has previously served as the chair of the Faculty of Science from 2010 to 2011. He has been head of a number of things, including the Electronics Materials Section, 2000-2006, the director for the Center of Electronic Materials and Devices from 2001 to 2006, and co-director of the London Center for Nanotechnology in 2001-2007. More recently, he's taken up what's called a pro-vice chancellor position, which by our terminology is a vice president of the university for research with a specialty in science and medicine. What's impressive about Tim's research is that it encompasses a wide aspect of electronic materials and devices, but as he'll tell you about today, his primary interest is in organic photovoltaic cells and why he is here. He's published over 250 peer-reviewed papers and has graduated a staggering 40 PhD students. So if you could join me in welcoming Tim to the department, please.
Tim, thank you very much for those kind words of introduction and also for inviting me to Toronto. I'm delighted to be here for a number of reasons. Firstly, I've only ever been to Canada once, which actually, given I travel a lot in my job, is quite remarkable. And I've only been through Toronto rather than stayed here, so that's great. Although it's rather cold. I think I picked the wrong time of year. I should have come for the PhD exam in August. Secondly, it's a great opportunity to meet Tim and others here. We talked last summer about collaborating. There's lots of areas of mutual interest and compatibility and synergy, from materials chemistry to making devices. And hopefully by the end of this week, we'll have identified some genuine collaborations, exchange of students and postdocs and so forth, which I think will be really exciting. And in fact, I brought one of my postdocs, Ian, who's in the audience. He's here to start initiating that collaboration. And I've had people from Tim's group coming over to Warwick already, which is great. The third reason, I'm going to just put my other hat on for one moment, as Pro-Vice Chancellor, is also interested in Toronto because one of the things I do is look at the research strategy of the university and develop that. And one of the things we've done is set up a collaboration with Toronto in New York. So those of you, I don't know if you know about this, but there's the Center for Urban Science and Progress, or CUSP. And it's a partnership between New York University, Toronto, Warwick, Carnegie Mellon, IIT Bombay, a number of industries such as IBM, Cisco, and so forth, and the city agencies. And we've set up this center there to look at the issues about the growing populations of cities, using New York City as a test bed, a living laboratory, so that you can look at the issues around how people work in cities. So it's a really exciting project, international collaboration, and it brought me actually in contact with your provost, who I've got to know quite well, and I'm seeing tomorrow. So that's another reason as well, which is good. So I think it's always useful, I'll spend a few minutes, most of you probably don't even know where Warwick is, so I've got a map. So the UK, somewhat smaller than Canada, clearly. So these distances between cities are relatively short, as I was explaining last night. So Warwick is located there. It's in the South Midlands, in the southern part of England, certainly the Midlands of England. It's 100 miles northwest of London, 150 kilometres. So it's an hour by train. Trains run every 20 minutes. It's an hour and a half drive from Heathrow Airport and so forth. So it's very well situated. It's 20 miles south of Birmingham, which is the second biggest city in the United Kingdom, and it's about 40 miles north of Oxford. So it's a really nice central location within the UK. A bit about the university. We're somewhat younger than Toronto, which has been around nearly 200 years, I think. It was only established in 1965, so the university celebrates its 50th anniversary in 2015. But it's grown very, very rapidly, not just in size, but I think I'm not being arrogant, say also in quality. And within the UK, it's now regarded as one of the very best universities, and it's also got a very good international reputation. So we have this obsession in the UK with assessments. We're assessed for everything. And we have this very laborious exercise called the Research Assessment Exercise, which takes place about every 6 years. It's now going to be called REF, Research Excellence Framework, and that will be this year. And Warwick came 7th overall across the whole university for research quality, and all the league tables were in that 6-7 bracket. It's quite a substantial university in size, certainly for UK standards. Again, it's quite a bit smaller than Toronto, but in the UK, the universities are generally smaller. So we have around 23,000 students, which makes it on the larger side for the UK. 10,000 or more are postgraduates, so it's very much a research-driven institution. Research-driven teaching underpins everything that we do, and it's very international. With a third of our students are international, and that means they come from outside the European Union. So if we included, I mean, England and Britain and the European Union have an interesting relationship, but if we just look outside if we included those countries within the European Union, then that number would actually be greater still. So it's a lot of international students, a very cosmopolitan university, 5,000 staff, and again, about a third of those academic and research staff are international. And so we're a campus university. It's a very nice campus. 50 years ago, that was what it looked like. It was literally fields, farmland in Warwickshire. It's now a very extensive campus with a lot of residential accommodation for students and some really nice infrastructure and buildings, and a very aggressive capital program, even in these times of austerity. So that's a bit of background on the university. I think it's useful just to explain where we come from. So I'm going to talk about solar cells and organic solar cells in particular, and this is the outline. I know this is a very general audience, so I've got quite a few slides, which is just an introduction to the theme. So those people who are specialists in this field, you can nod off or whatever. But hopefully what I say will be of general interest and will explain why we're studying what we're doing and what we think are some of the interesting challenges. I then got some results, which are a sort of snapshot of different things that we do in this field. And I'll focus initially on single junction cells, and I'll explain the terminology in a few moments. And in particular, something known as the donor-acceptor heterojunction, so the donor and acceptor are two different organic materials, and looking at electronic structure, and in particular, how we can optimize the open circuit voltage that we extract from the cell. So most of what I'm going to talk about today is about how we enhance the voltage of our solar cells, not the current, but the voltage. And there's various reasons we're trying to do that. And there's some work here on new materials and so forth. I'll then concentrate more on the electrode organic interface, which is equally interesting and challenging, and looking at some work with metal oxide layers, which I know goes on in this department here, organic interlayers, and again with a view to improving voltage, cell performance, and indeed cell stability. And finally, the third part, I want to talk about some more innovative architectures, multi-junction cells, which we're developing and others are developing to try and enhance the overall performance of the solar cells. Multijunction cells exist in the inorganic semiconductor solar cell world, but have been a relatively recent thing within organic semiconductors, and I'll talk about that. And there's a particular aspect of that where we're trying to develop very high voltage cells specifically for charging lithium-ion batteries for consumer electronics applications, and we've got a practical demonstration of that with some recent work. So it's a bit of a mixture of sort of materials chemistry, surface interface science, device engineering, and so forth. Something for everyone, he says. Right, so a bit of background. So as I said, for those who are experts in the field, please forgive me, but I think it's always useful to set the context. Solar cells, everybody's familiar with solar cells, but actually there are a range of different types of solar cells which are based on a range of different types of materials. And there are essentially three different types, and there are known as three generations of solar cells. First generation cells, here based on silicon. Polycrystalline, polycrystalline, multicrystalline silicon, the PN junction, been developed for a long time, pretty successful. In fact, the efficiencies are 20 to 25% really nowadays. Modules are 15 to 20%. They work very well. Long lifetime. If you buy a solar panel and put it on your roof, it's guaranteed for 25 years. And of course, silicon is abundant, so there's no problems there about the sustainability in that regard. However, it's still expensive. Silicon solar cells remain the bedrock of the solar cell industry. Probably 80% or more of solar cells that are sold in the world are based on silicon, first-generation technologies. But most of that deployment depends on government subsidies. So you only need an economic crash in Europe, Spain suddenly drops a subsidy, and the bottom goes out of the solar cell industry. So it's not still a sustainable industry, and the costs remain too high, even though silicon itself is a very abundant and relatively inexpensive material. There are also other issues. Silicon cells can only be fabricated on rigid substrates, so they have to be on glass. So that limits some of the applications in terms of integration into buildings and so forth, maybe transportation, where you might want flexible, lighter substrates, which would keep the cost down for the applications. And that's difficult with silicon, and is possible with other technologies. It's also actually pretty ugly. I mean, if you look at solar cells around your roofs, you fly in over Munich or something in Germany, you see all these solar cells on the roofs. It's aesthetically not very pleasing. So actually moving, which is an important issue for architecture. So in the long term, that could be a barrier to the deployment. The second generation, thin film technologies, also based on inorganic semiconductors, using materials such as cadmium telluride, copper indium gallium diselenide, cadmium selenide. There's also amorphous silicon, which isn't listed there. So there's a bunch of inorganic semiconductor materials that are deposited as thin films. So they use less material. These are thinner devices. So a silicon device would be hundreds of microns thick. A thin film device, maybe hundreds of nanometers thick. But because of that process, the crystalline quality of the material is poorer. There's more defects, and generally the performance goes down. So the best performances are in the 10 to 15% bracket. Still pretty good, and indeed there's a reasonable number of thin film solar cells sold commercially and installed for power generation applications. So fairly efficient, can be put on flexible substrates, so that's certainly a plus. But again, market penetration, it's still a subsidized industry, so it's still too expensive. And there are other issues. Some of these materials are really not very pleasant. So there's some sustainability, environmental issues that have to be addressed. Cadmium is highly toxic. Tellurium, it's not very abundant. I think it's something like the 78th most abundant element of the periodic table, which means actually there's not very much of it. Likewise, indium. So there are issues around, if you're going to put large areas of these solar cells around the world, you've got issues of sustainability and also the recycling and the payback associated with that. So there are practical issues there. Okay, then the third class, third generation cells, which are the least developed, both scientifically and technologically, are known as excitonic solar cells, and these are the cells I'm going to talk about today. They're based on organic materials, dyes. You've probably heard of the dye-sensitized solar cell. In fact, I know you had because Michael Gratzel, I think, was here giving a talk. So dye-sensitized solar cell, polymer materials, small molecule materials, and so forth. Really, research in this field only really started from about 2000 onwards. Efficiencies are now broadly in the sort of few percent regime, so lower again, 5 to 10%. The advantage is, in the long term, they use very, very low amounts of material. They use sustainable materials, lightweight. They're compatible with flexible, so plastic solar cells is a reality. And in principle, it should be a very low manufacturing cost. So if you can get the efficiency better, and perhaps more importantly, solve some of the stability issues, and there are issues which are being tackled but are still an issue, then this is hopefully a very promising technology. But it's still very much at that early stage. It's still in the R&D stage. It's not a commercial reality at the moment. So they're the three broad generations of solar cells. And horrible diagram. So you give undergraduate lectures and you say, never put diagrams like that on, nobody can read it. But actually, it's a roadmap. You don't need to get bogged down in the detail. There's one detail I am going to point out in a moment. But this is the solar cell performance roadmap, so certified solar cells from a national laboratory over a number of years, starting from the 1970s. And all the colors these different generations of technology. So the blue here, which has gone up progressively over the years, those are the silicon technologies I talked about, first generation. The green, these are the thin film technologies, so again, lower performance but improved steadily over the years. These here are actually, I didn't talk about these are concentrator cells, multi-junction cells, initially developed for space applications, but now being used or potentially used for solar farms in deserts. So they're expensive to make, but you use small areas and you concentrate the sunlight in order to get the high performance. So there's quite a lot of interest in that technology. And then down here in this box, these are the excitonic solar cells I referred to, so the third generation cells. So started really with a vengeance in 2000, but again, progress has been impressive as companies have started to develop the R&D side in this area, and in fact, it's blown up here. You can see performance is now of about 11%. In fact, I think there was a recent announcement of 12% for a polymer cell, I think. So progress has been very quick over a relatively short timescale. One more thing to point out, there's this lot here, which are inorganic sort of hybrid cells, and you'll notice University of Toronto's on there. So I thought I'd point that out for lead sulfide quantum dots. So Ted Sargent's group recently is on there. So there's a lot of research to do to improve the performance of these types of cells. So let's just rationalize some of the differences between the materials that are used in these solar cells. So the first and second generation cells, silicon, cadmium telluride, copper indium gallium diselenide, and so forth, those are inorganic semiconductors. And in an inorganic semiconductor, you have a high dielectric constant, a delocalized excited state with a very low binding energy, 0.01 eV, something of that order. And so separation into free charges, into electrons and holes, so you can generate a current, is a very easy process. It's a facile process. And so the PN junction, which is used throughout the electronics industry for silicon and other semiconductors, is the bedrock of the inorganic solar cell. Now, in an organic semiconductor based on molecules or dyes or polymers, then you have a quite different set of physical characteristics. You have a low dielectric constant, a highly localized excited state with a high binding energy, certainly above 0.1 electron volts, probably around 0.3 electron volts. So dissociation into the free charges, and I'll come back to this in a moment, is actually very difficult and is one of the challenges in building your device. So they call it, because that dissociation is such an important step, we call it an excitonic solar cell device. And so what you can't do is simply say, well, I'm going to make a PN junction in the same way that you do with silicon. You can't do that with organic or excitonic cells. You have to combine different materials with different energy levels, different functionalities, etc., in order to make a practical device. There's one further point which is important, that this excited state, this exciton that's generated, has a very low diffusion length in organic materials. So if you take a polymer, the diffusion length will just be a few nanometers. You may get up to around 50 nanometers for a reasonably crystalline material, such as pentacene, but it's still very low. And again, that places some constraints on the design of your device. So a little cartoon about how an organic solar cell works. So this is the simplest type of organic solar cell. We have two electrodes, one transparent, so the sunlight's going to come in through here. That's typically indium tin oxide, but it could be another transparent conducting electrode. We then have two organic materials. So remember I said a donor and an acceptor. So we have an electron donor material here in purple, an electron acceptor material here in yellow. Both of these are organic materials typically. And then you'd have a reflective metallic contact, typically aluminium. Again, you could use other metal electrodes. So in the basic device, you have sunlight. In the donor, in this case, it could be in the acceptor. We generate our excited state, our exciton, our electron-hole pair, which is highly localized, remember from the previous slide. So the first step is the generation of the exciton, strongly bound. Now, in order to extract charges, that exciton has got to get to an interface. There's got to be a driving force to dissociate the exciton and separate that electron and that hole so we have the free charges to generate our current. So the next important step is diffusion of the exciton to that interface between the two different types of materials. And remember I said the diffusion lengths is low, a few tens of nanometers at most, so that places some constraints on the thickness of those layers. You can't have them too thick. Provided you then have an energy offset at that interface of sufficient magnitude to overcome the binding energy of the exciton, then the charges will separate, travel through the respective materials to the electrodes, and then they're collected. Oops, that's what I meant to do, like so. So that's the basic operation of an excitonic solar cell. Generation of the exciton, so absorption of the light, diffusion of the exciton to the interface, so you have to have these interfaces between different materials, and those interfaces have got to have the right energetics in order to dissociate the exciton, and then transfer charge carrier mobility to the electrodes to generate the current. So a very different operation to a conventional PN junction silicon solar cell. You could use polymers, conjugated polymers, and there's some very successful work done based on polymer materials or polymer molecule combinations. Or you can use small molecule materials, which is actually the basis of what I'm going to talk about today. And I'll go through an example. I'll show a slide of some of the materials that we use in a moment. And basically the way, so these are called small molecule cells. And again, this is our typical device. So in this picture, the green is the electron donor, the yellow is the electron acceptor. Here's our electrode, the indium tin oxide, so the light would come through the bottom here, and here's our metal contact on top. So that's basically replicating the previous slide. These are fabricated in a system like this, organic molecular beam deposition. So this would be, we've got two of these, typically around 10 or 12 sources within the chamber, so we can deposit a whole range of different organic, inorganic, or metallic materials within that system with a glove box and so forth. So it's a nice clean environment. So these are materials that have sufficiently high vapor pressure that they can be evaporated without decomposition. So they can't be too big, the materials. The molecular weight is limited. You can't do this with polymers very easily, but you can certainly do it with small molecules. And the advantages of this technique are you get, because it's a vacuum thermal evaporation process, you get very good control over the film thickness, composition, so you can mix layers very straightforwardly, and therefore the morphology. You can make the whole cell in this system. You don't have to transfer to other systems, so you can deposit the electrodes and any other materials all in the same system, which is very convenient. It's compatible with putting down lots of different types of materials, so you can make quite complicated cells, single multi-junction cells, which is more difficult when you're processing from solution, which is what you would do with polymers. And I think importantly for understanding, it's the same environment that you use for doing more conventional surface interfacial analysis techniques. So if you want to do photoemission, XPS, UPS, or scanning probe techniques, STM, or mass spectrometry and so forth, they're all vacuum-based techniques. And so you can start to try and understand the device, deconstruct the device to understand some of the basic principles. And again, that's very difficult with solution process devices. And finally, it's quite interesting that the community, organic electronics community, is really split in two camps. Polymers, solution processing, small molecules, vacuum evaporation. And the argument has always been that it's expensive to fabricate using vacuum equipment, and it's cheap using solution-based processing. I actually think that's nonsense. This is a very proven manufacturing process. If you take a crisp packet, look at the inside, it's got a metallic coating. That coating is put down in a vacuum system. How much is that bag of crisps? It's actually a very, very well-proven manufacturing process. And what the polymer people, and I've probably got polymer people who are going to attack me afterwards. What the polymer people will say, but forget to tell you, is you've got to put down all the other bits of the device. You've still got to deposit the metal electrodes, and you need a vacuum system to do that. So in fact, vacuum evaporation isn't necessarily an expensive route. And if you look at the most successful OLEDs, organic LEDs, which have been commercialized, they're not made by polymer solution processing, they're made using vacuum systems. So it's a proven manufacturing process. So just another aside on this, I said that the thickness of the device is thin. It's constrained by the fact that the exciton diffusion length is low. So these layers can only be a few tens of nanometers. So the total thickness of the active region here will be about 100 nanometers in total. So you're really using very low amounts of material, and these are very lightweight in comparison to some other solar cell technologies. So some typical materials. These are the sorts of materials we use. And people in the audience will recognize these, some people. So phthalocyanines, these have been around for a long time. They developed many years ago, some of the copper phthalocyanin and so forth, largely for the paint industry. But very good materials, good dyes, good absorbers, subphthalocyanin, some nice work we've done with that as well. So these materials absorb broadly in this regime from about sort of 500 up to about 900 nanometers, depending on the particular choice of material. These are commercially available materials, but clearly you can do different things with those materials to change the properties. Oligoacenes, things like pentacene and tetracene are also good materials, and in fact these materials are used quite a lot in transistors, organic transistors. They tend to pack in certainly a semi-crystalline way, so you get good charge mobilities in these materials, and again, these absorb somewhere in the sort of 500 to 800 nanometer regime. Fullerenes, ubiquitous electron acceptor, pretty low wavelength absorber, but used extensively in organic solar cells as well. But there's a whole raft of different materials that can be used, and if you're chemically, synthetically able, as Tim is here, I'm not, but I collaborate with people who are, then you can functionalize and change the properties of these materials in a very elegant way, which hopefully will produce better materials for solar cells. So I think this is the last sort of introductory slide, just to put in perspective how a solar cell, the sort of characteristics of a solar cell. So these are the things I'll refer to when talking about the results. In solar cell, we characterize all that. When I showed those plots, you put them in a solar cell simulator, like here, a calibrated simulator with different filters. You can, the standard is AM 1.5. So this is the spectrum. And basically, you take the current voltage characteristics of your cell. So in the dark, it would be a diode, like so, the dashed line there. And then under illumination, you'd get the solid red line here. And the key characteristics that we're interested in are the short circuit current, so the current here at 0 voltage, and the open circuit voltage, the voltage here at 0 current. And the bit of interest for a solar cell is this fourth quadrant here, which is blown up here, so it's the blue now. So again, we have the short circuit current and the open circuit voltage. Now, another parameter that's important is the maximum power. So this is the power density. So this is the maximum power defined by the maximum voltage and the maximum current. And we can define something known as the fill factor, which is the ratio of the maximum power defined by Vm and Jm divided by the power defined by the open circuit voltage and the short circuit current. And basically, the squarer the JV curve is, the higher the fill factor. And ultimately, you would like a fill factor of 1, but in reality, fill factors for organic cells are of the order of about 0.5, 0.6, at best 0.7. So the power conversion efficiency, which is the number that I was referring to on that NREL chart of solar cell performance, the power conversion efficiency is then proportional to the open circuit voltage, the short circuit current, and the fill factor, all normalized to the incident radiation power. So the four parameters characteristics that you're interested in are the power conversion efficiency, and in order to enhance that, to maximize that, you need to maximize your voltage, your current, and your fill factor. Now, what I'm going to concentrate today, as I said, is mainly on the voltage, not so much on the current. We're trying to ramp that up, because traditionally the voltages in organic cells were down around 0.6, 0.7 volts. We've been trying to get much higher voltages for reasons that will become apparent later. Okay, so let's start with single junction cells. So open circuit voltage. So this is our nice schematic of a donor acceptor heterojunction, interface in between. And the open circuit voltage, there's been some debate for several years about the origin of that voltage, but in essence it's related to the size of this energy gap, this interface gap energy here, Ig, which is the difference in energy between the highest occupied molecular orbital of the donor, the HOMO of the donor, and the lowest unoccupied molecular orbital of the acceptor, the LUMO of the acceptor. And that defines the interface gap. And the maximum voltage you can extract is basically the interface gap energy minus some loss, which is essentially related to the binding energy of the excitons. In other words, the energy needed to dissociate the excitons at these interfaces. So the offsets here between these energy levels. So in order to maximize your voltage, you need to maximize your interface gap, remembering that these offsets have to be high enough to dissociate the excitons. So it's a compromise between those different energetics. Now, one of the things that surprised me when I started working in organic semiconductor, my background is in an inorganic semiconductor world. I actually started off with 3-5 semiconductors many years ago, and there's a very rigorous, the development of devices went hand in hand with very rigorous understanding of the properties of the materials. And the two went in a nice pace. Interestingly, I think the organic devices, the device area expanded very, very rapidly. And in fact, there was very little fundamental characterization of the properties of the materials. And I think it's only now that people are beginning to catch up and apply techniques which are commonly used in other materials, inorganic semiconductors, to understand the properties. And in fact, if you read the literature, many of the numbers for energy levels and so forth that are bandied around in the literature are just blatantly wrong, actually. And it's largely because there hasn't been that fundamental characterization to go hand in hand with the development of devices. So one of the things we've done quite extensively is just to do photoemission spectroscopy, a very standard technique in inorganic semiconductors and other areas, just to characterize the energy levels of these materials, which is something to understand the interface gap energy and then rationalize the open circuit voltage and hopefully maximize that. So this is just some work done 2 or 3 years ago. And as I said, the beauty about small molecules is you layer the materials in your evaporation process, so you can just do measurements using techniques such as photoemission on your device structure as it devolves. And this is just some measurements for ITO, phthalocyanine, chloroaluminium phthalocyanine, and the fullerene C60. So this is the donor, the chloroaluminium phthalocyanine. C60 is the acceptor. Using, in this case, these were synchrotron measurements done at Brookhaven, but you can do lab experiments as well, looking at the vacuum level shifts as you build up your device, but also looking at the valence band structure and the onset of the HOMO levels, which you need in order to understand the energetics. And out of that, you can draw energy level diagrams. And this is a methodology that's well known in the inorganic semiconductor world, but really hadn't been done much in the organic world. As I said, people are now doing this with some rigor, which is great. So this is the energetics for that particular combination of materials. And there's a number of things here, but the point I want to concentrate on is that the interface gap energy, which is this energy here in red, the difference between the HOMO of the phthalocyanine and the LUMO of the fullerene, is 1.15 electron volts based on that data for this particular material system. So clearly the open circuit voltage will be somewhat less than that because you've got some losses associated with dissociating the exciton. So this just shows some same set of measurements or summary of data for 3 different phthalocyanines, the ones that I actually showed in the schematic a little while ago. So copper phthalocyanine, chloroaluminium phthalocyanine, subphthalocyanine as the donor, and then having a common device structure. So C60 is the acceptor. These are the device results, the current voltage characteristics, and these are the schematics of the energy levels. So a Same acceptor, C60, different donors, different energy levels, so the HOMO goes down as you go from copper phthalocyanine to chloroaluminium phthalocyanine to subphthalocyanine, and the interface gap energy goes up. So for copper phthalocyanine C60, it's 1 eV. For subphthalocyanine C60, it's 1.75 electron volts. The current voltage characteristics, this is a summary of the data, the current, the voltage, the fill factor, the efficiency, those 4 characteristics I talked about earlier. So voltage I just want to focus on. You can see it goes from 0.5 up to 1.08 for subphthalocyanine. In other words, as we increase the interface gap energy, we're increasing the voltage as you'd expect. So that's just proof that it does work, although there are quite significant losses. You can see 1 EV yields a voltage of 0.5. Out here we have a 1.75 EV interface gap energy, and we're only extracting a voltage of nearly 1.1 volts. So there's some very significant losses that you need to try and overcome to enhance the voltage. Now, as I said, it's important you want to maximize the interface gap energy to maximize your voltage, but you can't just keep doing that because you'll sacrifice this ability to have offsets needed to dissociate the excitons. So again, it's this compromise between these energetics. So we explored the use of subphthalocyanine as an acceptor as opposed to a donor. So we replaced the C60 in our device. And the reason for doing that, if you look at the energetics here, this is 2 different materials. Tetrazine now is the donor. C60 is the acceptor. And in this particular configuration, all this data again came from photoemission experiments. Then the interface gap energy is limited to about 1.2 electron volts. And that's simply because of the energetics of the C60 mean that you've always got such a large offset here, which gives rise to those losses, big losses. So the voltage will be limited. So what we decided to do is replace the C60 with subphthalocyanine, because if you look at the energetics, we get a very large interface gap energy now of 1.9 electron volts, and the offsets are low, much lower, but should still be large enough to induce the dissociation, which should then hopefully give a larger voltage. And this is just proof that both materials are contributing to the photocurrent. These are external quantum efficiency measurements for a tetrazine C60 device here. This is the tetrazine absorption, and the tetrazine subphthalocyanine device. So this is the tetrazine absorption, and this is the subphthalocyanine absorption. So those are the current voltage characteristics for tetrazine subphthalocyanine cells. So tetrazine C60 here gives a voltage of 0.76 volts. So it's limited by that relatively low interface gap energy. But if we replace the C60 with subphthalocyanine, we get a much higher voltage. So we're now up at around 1 volt for a 14 nanometer layer. But if we increase the thickness of the subphthalocyanine layer, that goes up to 1.24 volts, which is now a pretty high voltage for an organic solar cell. And the performance overall increases because of that increase in voltage. So if you tailor the materials, you can now use materials that conventionally have been used as donors, as acceptors or vice versa, in order to optimize some of the parameters of your solar cell. And one actual advantage of this, I don't have the plot here, is that sub-PC is much more stable than C60. If you look at the stability of devices with C60, they degrade very rapidly without encapsulation, whereas the devices without the C60 are actually much more stable in this particular case. But the key point here is you can increase the voltage very significantly. So we took that another step. This is doing things very similar to what Tim's been doing here, where we think, well, okay, can we manipulate these materials and improve the voltage even higher? So again, this is our sub-PC C60 device. There's the benchmark with a voltage of 1.1. If we now use a sub-PC donor with a sub-PC, halogenated sub-PC acceptor, we can drop those energy levels through synthesis, if we get the right material, and in principle, we can enhance the interface gap whilst balancing the need for a sufficient energy offset in order to dissociate the exciton. So this requires some synthetic control of an existing molecule to see what voltage we can achieve. So these are three materials that a colleague of mine at Warwick, Mike Shipman, made. Made a family of subphthalocyanine, so it's taking the basic molecule, the trifluoro substituted, hexafluoro substituted, and a hexachloro substituted subphthalocyanine. Again, this is the energetics based on photoemission. So as you go across this diagram, the interface gap goes from 2.1 eV, which is very large, down to 1.8 eV, which is still quite large, but importantly, what you see here on the left-hand side, there is really no energy offset. You can't dissociate the excitons very efficiently. So that device is just not going to work in a very practical way. You might have a high interface gap, but the rest of the energetics don't work. Whereas if we go across this diagram, then we have both good energetics for the dissociation and a high interface gap energy. And that does indeed translate into good performance, otherwise I wouldn't be showing you. So the example devices are shown here. This is our control device, subphthalocyanine C60 with a voltage of 1.1. And as we go across, we see the sub-PC with the hexachloro derivative gives a voltage of 1.31, which certainly at the time it may still be, I think, the highest voltage recorded for an organic solar cell using essentially the same class of materials, but one substituted with these 6 chlorines. Respectable performance. The current drops a little bit. We'd like to enhance that, and therefore the overall efficiency drops a little bit because of that, but it's the increased voltage at the time we were interested, and again, as I said, increased stability. So you can, by understanding the energetics of these systems, develop combined materials in interesting ways to get the characteristics that you want. Okay, so I want to talk a bit about the electrodes. I've talked essentially about this interface, which is very important for device behavior, but also the interfaces with the electrodes are also very important. And you've got 2 electrode organic interfaces. You've got the interface between the donor and the transparent conducting electrode, which is typically indium tin oxide, and the interface between the acceptor and the metal, which is typically aluminium. Now I'm going to concentrate on this interface. It's the one we've done the most work on, the ITO donor interface. Now there's a number of different materials you can use for making more efficient extraction of charges at those electrodes. So for example, if you were to look at the electron extraction, you'd use materials such as zinc oxide, which is very efficient and works very well, titanium oxide, or an organic material such as BCP. To extract the holes, good materials include molybdenum oxide, vanadium oxide, organic materials such as PDOT, PSS, and again other materials, self-assembled monolayers and so forth. High work function materials are all quite efficient in enhancing this process. I'm just going to show some results for the metal oxides just to show how that works. So here's our basic device again, single junction device, phthalocyanine donor, C60 acceptor. So we'll go back to the simple devices at the beginning. And now what we're going to do is just insert a very thin layer of a metal oxide, molybdenum oxide in this case, at the interface between the indium tin oxide and the donor, the chloroaluminium phthalocyanine. There's a number of reasons why you want to do that. You want to extract the charges more efficiently, but also indium tin oxide is actually a very unstable material. So it's a big problem in the degradation of devices. It's not a very uniform material. You can buy ITO from the same manufacturer and it's got quite different properties. So actually eliminating indium tin oxide, or at least modifying the indium tin oxide, is a crucial element in making good devices. These are the current voltage characteristics for the devices with and without molybdenum oxide. So in the case of the red curve, that's without the molybdenum oxide, you get a voltage of about 0.5, reasonable current. in the case of the chloroaluminium phthalocyanide device. If we put down a thin layer, 5 nanometers of molybdenum oxide, then the voltage goes up very significantly to around about 0.8 volts. The current remains essentially the same. If you go too thick, in this case 50 nanometers, then the voltage is fine, but the current now drops very significantly because the very thick layer prohibits good charge mobility to the electrode. So there's a compromise of the thickness of the molybdenum oxide you can use, and 5 nanometers actually is the optimum for these particular devices. Now, we looked at that in combination with a number of different donor materials to see whether you could improve all these devices just by inserting molybdenum oxide, and the answer is some yes, no, others. So if we take chloroaluminium phthalocyanide with or without molybdenum oxide, then you do improve the voltage quite significantly and therefore the efficiency. If we take our subphthalocyanine donor with and without the molybdenum oxide, again, you improve the performance from 0.8 to 1, and again, you improve the efficiency. If you take copper phthalocyanine, however, there's essentially no change in the voltage. Arguably, it goes down a little bit, and therefore the efficiency remains unchanged. So there's no advantage to using the molybdenum oxide. And in fact, indeed, if you look at some of these different donor materials here, pentacene is another one, which also leads, in fact, to a reduction in voltage, a poorer performance when you use the molybdenum oxide. And we can rationalize that, and I'll come back to the energetics associated with these different materials. So subphthalocyanine, chloroaluminium phthalocyanine have deep-lying donor levels. And then as you go to copper phthalocyanine and pentacene, they're not. They're higher-lying donor levels. And you have to look at where they are with respect to the energetics of the molybdenum oxide. So the first point, is there anything about the morphology that you're changing? And this is just showing AFM images of bare indium tin oxide and an indium tin oxide with a thin molybdenum oxide layer on top. No change. It's only a 5 nanometer layer, so morphology is not important in this regard. These are Kelvin probe AFM images of the same surfaces before and after molybdenum oxide coverage, and you do see some very significant changes. First of all, the work function increases very significantly when you put down the molybdenum oxide. But also what you find is that the electrical properties of the surface are much more homogeneous when you coat the ITO with molybdenum oxide. And these defects that you see here in the bare ITO, which are very common in ITO surfaces, essentially disappear when you put the metal oxide on top. So you're producing a much more uniform electrical surface for your device. Remember, I said that ITO is one of the limitations in the performance of these devices. So it's not a morphological effect, but there are some significant changes in electronic properties. And in fact, one of the key points can be seen in the photoemission of the molybdenum oxide. So these are, again, photoemission results as a function of molybdenum oxide thickness up to about 20 nanometers. Again, looking at the shifts in the work function as you go from bare ITO to a molybdenum oxide coated film. And then the valence band structure shown here. And what you start to see are the appearance of these gap states just below the Fermi energy. And I'll show you some results for vanadium oxide which show a very similar trend. Gap states around 0.4 electron volts below the Fermi energy. And if you do analysis of the XPS data, the molybdenum oxide, there are oxygen vacancies, and it's a reduced molybdenum trioxide phase, which is why we tend to call it MOOX, because the stoichiometry is very variable. So schematically, what we think is happening is the following. If you take this is the energetics for this system, ITO, molybdenum oxide, and then a phthalocyanine, such as subphthalocyanine, which has a deep HOMO level below the gap states of the molybdenum oxide. There's an interface dipole leading to band bending at this interface and efficient hole extraction to the indium tin oxide. So the molybdenum oxide layer enhances the extraction of holes to the electrode. It improves the performance of the device. If you take an organic donor which doesn't have these deep-lying HOMO levels, such as copper phthalocyanine or indeed pentacene, in which case the HOMO is above these gap states, then there's no driving force, there's no band bending, there's no driving force for improved charge extraction, and the performance, if anything, gets worse when you include the metal oxide layer. So these metal oxides only work when you have the right combination of inorganic and organic materials. You can't just insert them for all materials, they won't necessarily lead to improved performance. What they will lead to is improved stability, irrespective of the organic materials you use. And this just shows, I can't remember which devices they are, which materials, but it just shows normalized efficiency of a device with and without the molybdenum oxide over a long shelf lifetime of hundreds of hours, and also under constant illumination in our solar simulator. And what you see is that in bare ITO you get quite a dramatic decrease in efficiency, whereas there's a relatively small drop in the case of the molybdenum oxide device. And that's even more pronounced when you're under constant illumination, so you leave your cell under constant irradiation in the simulator, which is quite an extreme condition actually, for hundreds, thousands, minutes. And again, you see the drop-off with the bare ITO is very, very dramatic, but with the molybdenum oxide, it's much less so. There's still a decrease, but it's a less pronounced effect. So much greater stability when you insert this layer at the interface. Just to show that the same results occur with vanadium oxide, we did the same thing here, putting vanadium oxide in a sub-PCC60 device. Again, these are the current voltage characteristics with a very thin layer of vanadium oxide, much improved compared to without. And again, when you look at the photoemission, it's the existence of these gap states that appear. This is a 5 nanometer layer just below the Fermi energy, which allow efficient charge extraction. Okay, so for the last few minutes, I want to just spend a little bit of time on multi-junction cells. This has been the driving force for wanting to increase the voltage in our particular case. So these are our typical single junction cells, and to make a multi-junction cell, you just connect them, and the best way of doing that is to stack them on top of one another, and in series you sum up the voltages of our two subcells. So we have subcell 1 with a voltage V1, subcell 2 with a voltage V2. Add them together. In principle, if everything works, you should get the sum of those two voltages, and so you get a much higher voltage and hopefully much higher performance. The trick is to make sure the recombination layer works. That's a very important part of the device. It's not just a matter of stacking these things on top of one another. You're generating charges in both cells, both subcells, so you have an exciton in both cases, and you need to make sure that the charges here recombine in this layer, and you're only collecting, of course, the charges at the two extremes of the device. So that recombination layer, tuning that layer is very important in order to balance the currents in these particular subcells. So the architectures can be quite complicated. There are different ways you can make a multi-junction cell. One is by using subcells that have very different organic materials that absorb in different parts of the spectrum. So you have one subcell here with one absorption, another subcell here with a different absorption, so complementary absorption. So for example, a C60 chloroaluminium phthalocyanine cell and a C60 subphthalocyanine cell, they would be complementary. Or, and there's reasons why you might want to do this, you actually combine cells that are basically absorbing the same spectral region, and that's the approach we've adopted for the high voltage work that I'm going to talk about. So you might use subphthalocyanine and CL6 subphthalocyanine, which basically absorb the same part of the spectrum in order to make your device. This is just to show the recombination layer. This is some work. So again, two subcells. So these are quite complicated structures now in terms of the energetics. Recombination layer here in the middle. We're using silver particles. Deposit silver, it's just evaporated. And this just shows how the device characteristics change with silver coverage. So these are nominal thickness. Of course, it doesn't go down as a monolayer. But what you find is that the current here in red maximizes for a nominal thickness of 3 angstroms. And in fact, what happens if you look at the electron micrographs of these materials, it's just silver clusters embedded within the organic matrix. If you have too thick a layer, then of course you're going to lose transparency and so forth, and the device fails deteriorates quite significantly. But optimizing that recombination layer is critical for balancing the currents in the 2 subcells. So the device architecture we focused on in particular is quite an interesting one, where we're stacking lots of junctions of subcells with a view to getting a very, very high voltage. And most of the cells are made of materials that have the same absorption. So if we look here, HJ is heterojunction, but these are subcells really, subcell here, here, and here. They're based on the same materials, subthalocyanine, Cl6 subthalocyanine, so they're basically absorbing in the same region. And we're stacking very, very thin layers on top of one another, each one with a recombination zone based around silver nanoparticles, BCP, and molybdenum oxide in each particular case. If you're going to put together a device like that, you don't just want to do it experimentally, you need to model it. There's a lot of parameters to get right. So fortunately in our group we've got somebody who's a lot of expertise in optical modeling in our device. So we can look at both the absorptance for the different layers as a function of layer thickness and so forth, and also the subcell current density that you extract. And these are just looking at the absorptance for a 3-junction cell, a 4-junction cell, and a 5-junction cell as a function of wavelength. And here, these are the modeled subcell current densities, again for a 3, 4, 5, 6 heterojunction device. So you can see that as we go along the numbers of junctions, then there's variations in the current. And importantly, as you increase the number of junctions, the range of currents in the different subcells starts to increase quite significantly. Remember, you've got to match the currents in your device, so that's not a good thing. So if you go to a 6-cell device, then you've got quite a significant range of currents of about 0.56, whereas in a 3-junction device, the range of currents is only about 0.1, which is much more the sort of value that you'd want. And these things in bold are the minimum currents, because ultimately it's the minimum current will be the current you extract experimentally in your device. So modeling these things is really important, saves an awful lot of time in terms of the practical issues around making your cells. So this just shows the results for some cells. So these are square centimeter cells in this particular case. So these are the current voltage characteristics as a function of number of junctions. So the single junctions here are shown in green and purple, and they give voltages of 1.1 and 1.32. And then what we've done here, we see the results, the current voltage characteristics as the number of junctions increases. And the voltage goes out further and further as you increase the number of the number of cells. So the results are summarized here. So a 3-junction cell is about 3.4 volts. 6-junction cell is now over 7 volts. And the numbers in brackets are the ideal voltages you would get if you summed up the voltages of the independent cells. So it's pretty close. You're seeing a slight reduction, but it's pretty close to the ideal value. So that's a very high voltage in a single cell. The currents extracted, they start to go down as the device gets more and more complicated, and we now need to work on that to improve those currents. But again, the numbers in brackets are the modeled minimum currents I showed you in the previous slide. So again, the difference between these currents is really not very significant. So again, validates the modeling that you have to do to optimize the device. Pretty good fill factors for such a complicated device, around 0.5. And the efficiency is pretty good, remembering that the currents are quite low. It's the voltage we're trying to enhance. So why do we want to do that? Well, the reason is if you take consumer electronics and lithium-ion batteries, although I don't want to put it on a Boeing, maybe, but Dreamliner. But compatibility, the charging range for a lithium-ion battery is typically around 4 to 4.2 volts. So if you can have a cell, single cells that are operating at voltages at least compatible with that, then that should be very attractive for application. So this was just to demonstrate that it does work. If you take, we're now plotting the efficiency as a function of operating voltage of our cell. So if we have a 4-junction cell, then the voltage, the operating voltage, is clearly below the charging range. So 4 junctions isn't enough. But if we go up to 5 junctions, of course, now our voltage is higher, as I showed previously. It's quite a significant higher. This is done under 1 sun, but now quite significantly higher than the amount needed to charge. And interestingly, that voltage is maintained even when you reduce the power of the simulator. In other words, as you go to darker and darker conditions. Because remember, you're not always going to put something out in bright sunlight. You want it to work in cloudy conditions or even indoors. So if you go down in power, so calibrated, the standard is 100 milliwatts per square centimeter. All the current voltage curves I've shown you, that's the standard. That's really compatible to putting your cell outside in sunny conditions. But as you reduce the power, even at 10 milliwatts per square centimeter, you've still got a voltage that is sufficiently high to power your device. So the voltage doesn't decay very significantly. So that's very important. So just to show it works, this was just a simple lab-type demonstration, taking a 0.7 milliamp battery. Show here the charge current as a function of charge time. So for a 5 heterojunction device, which gives us this high voltage, the voltage necessary to charge. And what you see is under 1 sun, under 100 milliwatts per square centimeter, then charging is complete in 1 hour. So if you put your cell outside, it would be complete in an hour. Whereas if you drop the power, you go cloudier and cloudier in effect, then obviously it takes longer and longer to charge. But even using an LED, green light, 530, it only takes, 3 hours? And obviously lots and lots of hours as you drop down to about 10 milliwatts per square centimeter, but 12, 14 hours, you'll still get that charging. So that, because that voltage is maintained. So we think that's really quite a nice illustration of how you can use these cells for doing something practical, charging something for consumer electronics. And actually one of the key things is to trickle charge your device. We're always plugging, I don't know about you, but I've got more adapters in my bag than I've got clothes when I came to Toronto. You're always putting in your devices, plugging them in, whether it be your iPad, your iPhone, your Mac, your laptop, etc., because we're just using, they're just power intensive. And if you can trickle charge them, keep them going, you don't have to keep plugging them in. So in conclusion, I've looked at single cells, I've shown you work on single cells and on multi-junction cells using, and hopefully shown that by understanding some of the fundamentals of the device and the materials, and by choosing the right combinations of materials or synthetically modifying materials, you can A, understand and B, optimize some of the important parameters that affect the performance of the cell. I've shown a wide range of examples, including this last example, which is quite an innovative architecture for practical applications. More importantly, I personally find it very interesting. There's lots of research still to be done in this area, both from a sort of chemistry, materials chemistry way, but also in a device engineering way, in order for these things to become practical technologies, but I'm convinced they will in the future. I think there's a very real need for low-cost, very practical solar cells. So on that note, I'll acknowledge a number of people. As always, lots of people do the work. These are people in my group who've done various aspects. Ian is here with me in the audience, so he will correct me if I answer the questions incorrectly. Number of very good collaborators in Warwick. Ross Hatton in particular on electrodes. We've done a lot of work on alternative indium tin oxide, two indium tin oxides using metal electrodes, transparent gold electrodes and so forth, which actually work very well. And he's been the driver behind that. Mike Shipman is a synthetic chemist on the subthalocyanines. Neil Wilson, we do a lot of work on atomic force microscopy with him in a collaboration. And Chris McConville on some of the photoemission. Kevin Smith in Boston is a very good collaborator, synchrotron measurements, and then a bunch of people as well in my old institution, Imperial, and in some companies. And these groups and companies provide the financial support. Thank you for your attention.